we're asked to find the Laplace transform, which is big F of s, of the function f of t equals t cubed. So looking at the definition of a Laplace transform here at the bottom, we have the Laplace transform of t to the third is equal to big F of s, which equals the integral from 0 to infinity of f of t, which is t cubed, times e raised to the power of negative st dt. Notice how here we have an improper integral, so we need to rewrite this using limit notation. This is equal to the limit as b approaches infinity of the integral from, instead of from 0 to infinity, we'd have from 0 to b, again because b is approaching infinity, of t to the third times e raised to the power of negative st dt. Now for our next step, we'll find the in-def integral of t to the third e to the negative st with respect to t. Then we'll come back here and find the def integral and then determine the limit. For our next step, let's find the integral of t to the third e to the negative st with respect to t. This is going to take quite a bit of work because we'll have to apply integration by parts shown here below multiple times. To begin, we'll let u equal t to the third, which means differential v is equal to e raised to the power of negative st dt. So we differentiate to find differential u, and we integrate to find v. The derivative of t to the third with respect to t would be 3t squared, so differential u equals 3t squared dt, and now we need to integrate both sides of the equation here to find v. So we'd integrate e to the negative st with respect to t. This requires u substitution where u equals negative st, differential u equals negative s dt. So dividing both sides by negative s, we have negative 1 over s differential u equals dt. So when we integrate here, we'll have an extra factor of negative 1 divided by s. V is equal to negative 1 divided by s e to the negative st. So applying the integration by parts formula, we have u times v, which would be negative 1 divided by s t to the third e to the negative st minus the integral of v du. Looking at v times du, notice how the product will be negative. Because we have a minus here, it becomes plus. And then let's write this as 3 divided by s. The integrand function would be t to the second e to the negative st dt. And now to integrate here, we'll have to perform u substitution again. So to integrate here, it'll be similar to what we did here, except now u equals t squared. So differential u equals 2t dt, but differential v is still e raised to the power of negative st dt. So when we integrate here to find v, we get v equals negative 1 divided by s e to the negative st. We need to be careful here though, because we're going to have 3 divided by s times the quantity uv minus the integral of v to u. So this first term stays the same. We have negative 1 divided by s t to the third e to the negative st, and then we'll have plus 3 divided by s times u times v is going to be negative 1 divided by s t to the second e to the negative st minus the integral of v du. Again, we have minus here. V times the u is negative, so this becomes plus. Let's write this as 2 divided by s times the integral of t e to the negative st dt. Before we integrate here though, let's distribute the 3 divided by s to keep things more organized. So the first term stays the same. Then we'll have minus 3 divided by s squared, t squared, e to the negative st. Then we'll have plus 6 divided by s squared times the integral of t e to the negative st dt. And now we'll perform integration by parts again here, where we'd have u equals t, so differential u equals dt, differential v is equal to e raised to the power of negative st dt. So integrating here to find v, we get v equals, again, negative 1 divided by s e to the negative st. So these first two terms stay the same. And we're going to have 6 divided by s squared times the quantity u times v. Well, u times v is negative 1 divided by s t e to the negative st, and then minus the integral of v du. Again, v times du is negative because we have minus here, it becomes plus. So we have plus 1 over s times integral of e raised to the power of negative st dt. Again, to keep things organized, let's distribute 6 divided by s squared here and here. So the first two terms stay the same. And then we have minus 6 divided by s cubed t e to the negative st plus 6 divided by s cubed times the integral of e raised to the power of negative st dt. Now to integrate e raised to the power of negative st dt, we've already done that several times up here. So the first three terms stay the same. So we have plus 6 divided by s cubed times the integral of e raised to the power of negative st with respect to t is negative 1 divided by s e to the negative st. And of course we have plus a constant of integration. Let's go ahead and find this product and write this one more time on the next slide. So for this last step to find the in-depth integral, let's change the form of these first three terms and then we'll find this product. So let's write this first term as negative t to the third divided by s e raised to the power of negative st. Let's write the second term as minus 3t squared divided by s squared e to the negative st. Let's write the third term as minus 6t divided by s cubed e to the negative st. And let's write this product as minus 6 divided by s to the fourth e to the negative st and then plus c. So this is the in-depth integral. Remember, our goal was to find this definite integral, then determine the limit. So now that we know the antiderivative or the in-depth integral, though, we can write this as the limit as b approaches infinity of negative t to the third divided by s e to the negative st minus 3t squared divided by s squared e to the negative st minus 6t divided by s cubed e to the negative st, and then finally minus 6 divided by s to the fourth e to the negative st. And again, the limits of integration are from t equals 0 to t equals b. And now we need to find big F of b minus big F of a. So we'll first substitute b for t. So we'll have the limit as b approaches infinity of, again, we're substituting b for t, so we'll have negative b to the third divided by s times e raised to the power of negative sb minus 3b squared divided by s squared times e raised to the power of negative sb minus 6b divided by s to the third times e raised to the power of negative sb, and finally minus 6 divided by s to the fourth times e raised to the power of negative sb. And now we substitute 0 for t. Notice all of these terms contain a factor of t except this last term. So these first three terms would be 0 because we'd have 0 cubed here, 0 squared here, 0 here. So we're just left with minus 6 divided by s to the fourth times e raised to the power of, this would be negative s times 0, which would be e to the 0. And now let's determine this limit on the next slide. Now to determine the limit as b approaches infinity, if we needed to, we could write these first four terms by moving the exponential term down to the denominator. For example, in this first term, we could write this as negative b raised to the power of 3 divided by s times e raised to the power of positive sb. To determine the limit as b approaches infinity in this form, we may need to apply L'Hopital's rule several times, but the limit will be equal to 0. So these four terms all approach 0 as b approaches infinity. So we're just left with minus negative 6 divided by s to the fourth times e to the 0, which is 1. So this limit is equal to negative and then negative 6 divided by s to the fourth which gives us positive 6 divided by s to the fourth, which is the Laplace transform of f of t equals t to the third. So to summarize, the Laplace transform of t to the third, which equals big F of s, is equal to 6 divided by s to the fourth. So going back to our first slide, again we now know big F of s is equal to 6 divided by s to the fourth. Now this was quite a bit of work, and just like there are formulas for derivatives, there are formulas for Laplace transforms. So it would have been much faster if we use the Laplace transform formula shown here, where if we have f of t equals t to the third, then n equals 3, which means the Laplace transform, big F of s, is equal to 3 factorial divided by s raised to the power of 3 plus 1, or s to the fourth. So again, knowing that f of t is equal to t to the third, we can quickly determine the Laplace transform of t to the third, which equals big F of s is equal to, we have t to the third, so n is 3, so we'd have 3 factorial divided by s raised to the power of 3 plus 1. Well, 3 factorial is 3 times 2 times 1 divided by s to the fourth, which of course gives us 6 divided by s to the fourth. So after we do several of these using the definition of a Laplace transform, we'll then just use the formulas to determine the Laplace transforms. I hope you found this helpful.